Okay, I think we could start.
Okay, now we are on YouTube. Sorry.
Oh, sorry. Michael, you need to make me a co-host.
Okay, sorry. Yes, I did.
Thank you. Can you see my screen?
Yep.
Great. So, hello everyone. Welcome to June edition of Space Cafe Tokyo. And we haven't been able to do it quite frequent, but hopefully we are hopeful by August we might be able to host it in Shimokitazawa again. And so maybe this month and July might be the last two versions we go online. Right. So today we are gonna cover a very interesting topic. This NASA mission called OSIRIS-REx mission to an asteroid called Bennu. I'll get back to that and the speaker in a bit. Right. But those who are joining for the first time, and also we have most of our audience is frequent participants. So the Tokyo Space Cafe started a couple of years ago, and usually we are live. We get together at this really cool British pub in Shimokitazawa, called Good Heavens Pub. And as you can see from these photos, it's very cozy place that we get together and have a science talk and over a beer. But unfortunately, because of the pandemic, we can't do that. And so we moved online since last year, around March, April, and we have been doing it online ever since. Right. And for the participants who are joining online especially on Zoom, uh, make sure to keep your mic and video muted. And you can ask questions on Zoom chat or the YouTube live chat. And then during Q&A, I will pick the questions and present it to our speaker today. And the Q&A might not be in the order that we get the questions. I might decide some questions to go first and then some for later. But please feel free to ask anything you are interested in from the speaker. Okay. Next. And I also want to introduce the Space Cafe Tokyo team. My name is Tilina. I'm a science communicator based in Tokyo. And then we have Ken. Ken, would you like to say hi?
Hey, everyone.
Right. And Ken is a researcher at the Tokyo. He's also Tokyo-based and working at IPMU. It's a research institute in Tokyo. And then we have Michael. Michael, can you say hi?
Hi, everyone.
And Michael is also a PhD student at University of Tokyo studying astronomy. And so three of us organized this edition of Tokyo's Space Cafe. But we also have a Japanese edition, which is organized by Ayako. And it's almost held monthly. Sometimes we share the same speaker, if the speaker can speak both English and Japanese. Right. And okay, so I want to introduce the speaker today, and he is Dr. Prasanna Deshapriya, but we all call him Desh as he prefers. There is currently at ENAF, which is the sort of like the National Observatory in Italy, and he's based in Rome, the Rome Observatory, and his research interest is focused on uh, these small bodies in the solar system, and he has worked with the European. There's a really famous European mission called Rosetta, which is very similar to JAXA's Hayabusa mission, like equal level of popularity among people.
OSIRIS-REx,
And
sorry, is the OSIRIS-REx.
okay,
Which is-
OSIRIS-REx, and then he studied his BSc, his undergraduate in Sri Lanka in University of Colombo, and then after that he went to he did his masters in Vietnam and also in France at the Observatory of Paris, and then he followed up with his PhD at the same observatory, and now he finally has ended up in Rome and working on this OSIRIS-REx space mission, which is a very cool space mission where the mission goes to an asteroid and takes samples and return to Earth. And interestingly, the mission is actually, most of the mission is done. Now it's on the way back to Earth, and supposedly sometime in 2023 it should be back. So Desh will discuss and present today some of the results and some of the understanding that we have so far. And I'm sure once we get the sample, we'll have so much more science coming out of it. And I'm sure Desh will be busy with that. So thank you so much. Desh, I give the floor to you, and let me unshare my screen, and then you can share your screen.
All right, thanks Tirena for the introduction and having me here. Let me see if I can get my screen shown to you guys. All right. Okay. Are you able to see my screen?
Yes.
All right, thanks again. Yeah, so I'm working at INAF. So INAF is the National Institute of Astrophysics in Italy, and Observatory of Rome is part of that. So I work on OSIRIS-REx mission and also on the near-Earth asteroids. Today I'm going to talk to you about this mission, OSIRIS-REx principally, and tell you about what we've learned from the mission so far. So I think probably you might have heard about the mission. It's a bit equivalent to its Japanese counterpart, Hayabusa 2 mission, which just delivered samples last December. So I think this could ring some bells to you. But otherwise, I'm just gonna continue and give you some idea about this mission is. So OSIRIS-REx mission is built on different scientific ideas and different focuses. So one is to understand the origin of the solar system, the formation, and how the life, as you know, came into being on the planet Earth, and also to help improve our understanding of asteroids spectrally using spectroscopy, and also it aims to probe about the asteroids as means of a resource, because these asteroids contain a lot of minerals which you could extract, and this could help in the future for interplanetary travel and also for future missions. And also there's an important aspect of security, because these objects could hit the Earth at some point, and there's some probability. So we also need to be careful about that. So this mission focuses about these areas, because as you know, 66 million years ago, the dinosaurs were destroyed due to its, an impact like this. So yeah, so this mission tries to answer different questions, and main objective though is to bring a sample from this asteroid Bennu back to the Earth. So I just here's an image of the launch which took place on 2016 September on the leftmost image, and these are two orbits of the asteroid Bennu and the Earth, with the Sun being on the middle, and the green dot is the Earth, and the Bennu is on red. So yeah, and we arrived at Bennu after about 2 years of travel in interspace in late 2018, and we collected the sample last year. So in October 2020, and now the spacecraft left the vicinity of the asteroid in a few months ago, about 2 months ago. Not yet 2 months, yeah, 1.5 months ago. And now we are on our way back to the Earth to arrive on the Earth 2023 in September. So here are the orbits of these objects, the Earth, this Bennu, and the spacecraft in different two views on the image on the left. So you could see that it's the orbit in the blue is the Bennu. It's bit is inclined to the orbit of Earth. So we had to do some orbital maneuvers to get there first. So we did some Earth flybys and change the angle of the orbital plane and before arriving at Bennu. And the images on the right, the two images are which like moving around in the middle, is a radar image actually. So Bennu was covered in 2019. This is a radar image from which we were able to reconstruct this 3D shape of the Bennu. Hello guys, are you able to hear me?
Yeah.
Yeah, I can hear, but the presentation dropped.
Yeah, sorry, there was some trouble. Yeah,
No,
sorry about that.
no problem.
I'll get back to the presentation. Okay, so as you can see here, so this is an image, radar image, so from which you were to reconstruct the 3D image of the Bennu using. So this
Sorry,
is
Desh,
this
we
comes
can't
to.
see the presentation. Can you share it again?
Ah, okay.
Right. Okay, it's coming. Right, now we can.
Okay. So, okay, I stopped. So I had to. Sorry.
Maybe if we stop your video, it might help the connection.
Okay. Is it okay now? Just give me some feedback, if you can, please. Let me see.
It says you
Okay.
started screen sharing, but we can't see yet. Okay, yeah, there we go.
Okay, maybe. Okay, great. Thanks a lot.
Yeah.
Sorry about it again.
Go ahead.
So yeah, so here you are seeing this 3D model we created from the radar data. So the radar data acquired by the Arecibo telescope in 2009. Yeah, thanks. 2099, and because of the how the orbits work, when it comes to Earth every 6 years, 2005 and 2011, we get the data, and we were able to create this 3D shape model. So it's about 500 meter diameter, as you can see here. So to give you an idea, I put this very famous building in the to give an idea. So it's even shorter than this sky tree. So this is a spinning top, and it spins the its north pole is on the south, so it's a retrograde rotator. So it's it takes about 4 hours to make one rotation around itself. And it's very dark objects, which has an albedo of, we call this term an albedo, 4% of albedo. So which means it reflects back 4% of sunlight, invisible sunlight that that arrives to it. And it's also a type B, spectral type B. So these spectral classes are sort of an carbonaceous in this family are made of carbon. And if you consider the meteorites, we could relate it to carbonaceous meteorites. So this sort of like comparison to understand the nature of its composition for the space mission. Okay, well, as you can see here in this timeline, so the mid 2016 term goes on to 2000 and further as the sample analysis progresses. So during this 2008, 2020, we were collecting a lot of data and how the asteroid, where to get this sample from, which is very important, possible areas. And so here is the suite of instruments we have, which help us to understand Bennu and the samples, where to get the samples from. So you have here a touch and go sample acquisition mechanism. So we call it the tag SAM because it's a touch and go maneuver. So you just
The presentation dropped, Desh.
yeah, okay, I see that. Okay, I try to get it back. Sorry again, guys.
No problem.
Let me know if it's okay.
Yes.
You are okay. Yeah. So here is the instrument payload. This is one of the shots taken before the launch of the spacecraft. So you have this here. A is the tag SAM, which helps to get the sample, and B is the OSIRIS spectrometer. So we have two spectrometers, OSIRIS and OTIS, which is C. So these help us understand the composition of the asteroid. And D is a suite of cameras, which have 3 different cameras. So to get very high resolution images of the surface, and also to get some images in different wavelengths, so using filters. So this is the Polycam and MapCam. MapCam uses the filters. Polycam gives higher resolution images of the surface, and SAMCam, which records the sample acquisition during the sampling event. And also there's a student-built instrument called RExSys, which is made by students at MIT and Harvard, which tries to understand the elemental composition using X-ray spectroscopy on the surface. And here the F is the sample return capsule. You are seeing this white circle here. And yeah, you have this usual instrument, high gain antennas, and also there's the Canadian instrument called OLA. So this is a altimeter based on laser technology. So you are like sending feedbacks and calculating the distance to the surface and and it helps to make us digital shape models and a 3D model of the asteroid. Okay, so OCAMs here is a technical chart of these spatial resolutions depending on the areas of the range to the surface altitude. And as you can see, here MapCam has, although it has a lower spatial resolution, it has colors, so the filters, which gives us the idea, understanding of the composition of the surface, whereas the Polycam has about 5 times better spatial resolution in its images. Yeah, so I would not go again. So I would just say that OSIRIS is a visible infrared spectrometer. So it works from about 0.4 to 4.3 microns. And OTIS is the thermal emission spectrometer. So it reacts to the energy emitted by the in thermal emission in longer wavelengths. And here is an image of a test we've done on the laboratory before launch. So here what you're seeing on the left is the sample head. So this is what would touch the surface, and this sample example gravel that would be similar to the regolith of the surface on Bennu. So regolith is sort of this loose material that is present on airless bodies like asteroids. So what is being done here is it's like a vacuum cleaner, but in the reverse sense, because there's no air. On the outer space, we send some air, so the nitrogen gas, from this instrument, and we give some energy to the particles around the surface, and we collect them, we absorb them through the sample head. So this is the tag instrument. So so this shape model I showed you before was before the arrival at the Bennu, and here on the rightmost image you can see the image that we recorded as we arrived at the asteroid in 2018 at the end. Here you can see a lot of details on the surface, and the shape model that was done using the radar data is quite compatible, we would say, and it also reproduced this sort of this ridge around the equator, the equatorial bulge, as we call it. So it was a good attempt at the shape modeling with radar data. And here is even an image with more details. As the asteroid rotates, you can see different different shades of colors. So there's sort of these bright areas, dark areas, and boulders. And imagine that we come for a sample return mission. This was sort of unexpected because from the initial assessments using the thermal infrared data, it was thought that this area, the asteroid would be with less boulders, but with a lot of dust around, like as you would see in a beach. But in the end, it's turned out to be quite challenging as we arrived. So we had to rethink how to approach this problem to get a good sample from securely from a very hazard-free area. So here is an image, one of those we've seen at the arrival. So here the resolution is about 33 centimeters per pixel. As a reminder, this is the size of the head of the tag stamp, so it's a bit more than 1 foot. So we were planning to sample 1 pixel from this image, just to give an idea. So this image also has a phase angle about 48, which is interesting because it allows you to see different structures and see some shadows of the objects near the terminator. So terminator is the area where the day and night separates the asteroid. So which you can see on the right side of the image. So so these were the first impressions as we arrived. And also we were able to see some big boulders across the object. And here is a map that we've done using this initial data. So we could still see some impact craters that are present along the equator, and also some boulders. And the idea of the mission was now to pick up a good area to sample. So there are first some candidates, but we started to get more and more data to confirm and understand the nature of this asteroid and the composition of these interesting areas before selecting the final site. So here are 2 images taken at a cadence of about 17 minutes. So as the asteroid rotates, you can see how this perspective of looking influences your idea of what you can see in the image. So on the image on the left, You can see here this structure here, which seems to be a crater. But it's more evident on the image on the right here, as the asteroid is rotated a bit further. You can see the shadow near the limb, which allows you to identify even the depth of the material inside, thanks to this shadow. And here is a image of the largest boulder that is found on Bennu. It's called the Ben. And this was interestingly one of the features that was resolved on the initial shape model. Yeah, another view of this rock, which is about 22 meters high here. Yeah, so these are some images that you can see. And yeah, so this was one of the first results we got from Bennu, which is the fact that Bennu has experienced aqueous alteration, which means Bennu is hydrated, or in other words, as this is a rubble pile, so these are the objects that would result from collisions between large asteroids in the main belt, and all the time they drift away or closer from their orbits to the sun. And that's how it ended up in the near Earth space, which is where Bennu is found today, although it was originated in the main belt. And so this is a remnant of these rubble piles, of these impacts that got reprocessed after this impact. And Bennu is one of those remnants from one of its mother body. And so we could say that during the time when this was in the main belt, because these objects in the near Earth space, they could not survive ages more than 10 million years. The fact that this lifetime is shorter than the life of the solar system, which is 4.5 billion years. So we could say that it's already something that's inherited from its parent body, which is not longer present right now. So these are remnants. And so in this plot here, you are seeing a spectrum of Bennu in the black color, and you are seeing its reflectance stays stable at from 2.2 microns to up to about 2.6. And then there's a sudden drop of the reflectance. So the curve drops a bit, and then it continues to get back to the continuum about 3.2 microns. So this drop is caused by the phyllosilicates that are present. So these are the silicates, the clay minerals, if you will, that were presented in the asteroid, the main progenitor of the Bennu. And because if at some point this material got heated up, so there was a point probably where these silicates and water was present in the form of ice, and because of the radionuclides, radioactivity of some elements that would, like aluminium-26, that would decay, it heats up the core, and then there was liquid water forming and reacting with this clay, which formed these features. So how do we know this exactly this? Because we know we have in our hand the meteorites from asteroids that come to the Earth and landed to the Earth. So we find some equivalents in meteorites, which you can see here have the same properties of this spectra. So from the meteorites, we could understand that this is a sign of water present in the past of Bennu. So this was very interesting results. And also we found that Bennu's rotation rate is increasing over the years. This is thanks to all the data that we accumulated up until the time of the mission from 1999 using radar data. And from this, you could constrain the orbital orbit and also the spin axis of the object. And for the smaller objects with low masses, unlike planets, there's this Yarkovsky and Yorp effects that come into play. And so this due to the re-emission of thermal radiation after the asteroid is heated up, so it re-emits the radiation, and then it creates sort of a torque on the asteroid that would, over the years of millions of years of scales, leads to slow down or increase the speed of its rotation. So here, in the case of Bennu, we are seeing it's speeding up using this data. And also we found that there are some albedo variations on Bennu. So here you are seeing different images with different features on the surface. So you are seeing some, and the four surface images on the right, you are seeing some boulders and some bright materials. So we see that there is about 3% to 15% of reflectance variations on the surface, and these are quite interesting. And this was very preliminary study, and after following on these bright features, it was discovered that these bright features contain material from different objects other than Bennu, because these spectral signatures of these objects resemble to those of the asteroid Vesta. So we have pyroxene bands that helped to identify this. So this reinforces the idea that a lot of objects got mixed and a lot of collisions were taking place even after the Bennu was formed. Or even it could be even some material that Bennu acquired during its reprocessing as a reply after the cataclysmic disruption after the collision in its mother asteroid. So here are some of the examples of these pyroxene-rich boulders. You can see on this map their locations, and you could see this characteristic band close to 1 micron that would that helps to identify this interesting results. And also we've also discovered that Bennu is getting closer and closer to the sun because its retrograde rotator, as it rotates around, it's due to this Yarkovsky force. So this is the asteroid that rotates in retrograde motion. So it's as it moves in a prograde orbit around the sun, so it re-emits its thermal radiation on this afternoon side as it's come to the night. So this this leads to a force which is called the Yarkovsky force, and for these retrograde orbiters, it leads to its energy to be lost. So this is it means that its semi-major axis would decrease, it decays over the time, and it has been observed from the data from 1999, 2005, and 2011. There's a measured to 160 kilometers drift from this 12 years alone that's responsible by the Yarkovsky force. So with this data, we could, and also including thermal emission data from the asteroid, we could make a thermal model and get using also a force model of the solar system. You could come up with a also density of the object. So that was also thanks to the first radar data, which helps us to create the shape model from which you could calculate the volume, and from this you could get the density. And it was this value 1.2 grams per centimeter cube. So this is a bit denser than water, but if you compare this with rocks that you find on the Earth, on the rocks, would be about 2 times or 3 times more. So this is very porous and very less dense rocks that's present on Bennu. And then this was confirmed using the data. Of course, as we arrived at the at the Bennu using our spacecraft data. You could measure the as spacecraft orbits Bennu. You could measure the variation of this orbit, and using this data, you could use the radio signal that was received at the Earth. You could come up with the gravity of the object, and then you could estimate the mass, and then using the more detailed shape model, you can get a better idea of the volume and then the density. So this is very good estimate compared to what was the previous value that was observed before the arrival at the Bennu. So this is very pioneering technique, and it needs a lot of skills, like you have to have a good Doppler tracking, and you have to have a good range measurements, and also have a good data of radar data to make a good shape model, and also a better understanding of Yarkovsky effect. So here is another study that I took. I was leading. So I started to study spectrally the craters that are present on Bennu. So this led to understand that the craters, as they are created on Bennu, are created spectrally red, which means that they as you move in the wavelength, they reflect more and more energy from the sun, and then they are more hydrated, and also they are brighter. So what you are seeing here on these plots is the diameter of the crater. So if you imagine craters are older and smaller craters are younger, so you could see on these plots there's a trend for the smaller craters, their reflectance is higher, so this is much brighter, and as they age, the reflectance sort of shuts off and joins the average value for Bennu, which is given in this horizontal line in black. And same goes for this spectral slope. So they become the smaller ones are redder, and they join the craters join the normal value of Bennu as they age. So the bigger ones have a similar value as the Bennu. And also, we also see that in terms of the 2.7 micron band depth, which characterizes the aqueous alteration on Bennu. So here we can see the smaller craters have a higher band depth, and the larger craters have a lower band depth that resembles that of average Bennu. And also there's a trend between sort of a positive correlation between the reflectance and also the band depth. And this on to the right, the histograms show that the majority of the objects are located. Majority of the craters are located where the mean value of Bennu is at in terms of spectral slope, reflectance, or band depth. And here is another result we've got about Bennu that was very unexpected. So we arrived at Bennu in late 2018, and even just after 1 month, we've discovered this sort of a bright material around Bennu. First, people thought that it was some stars that's in the picture, which was usual. But when you put the background stars, it was not where the stars would be. So it was a big puzzle, and it was interestingly discovered that Bennu is active, which means it's throwing material away. So these are some dust particles that have been thrown away from Bennu. So here you see some of these processed image directions of the emission of these particles. So which is very unprecedented for spacecraft discovery. And there came to be three main causes for this. So it could either be a meteorite impact. So these micrometeorites are like everywhere on the whole system, and they could impact. And if they would impact on some fragile material, it could leave. It could give rise to this observed dust, and also thermal stress could also cause this because of the 4.3 hour rotation period. The dark side gets very cold on Bennu, and after half a day it gets again hotter. And then because of this thermal stress taking over and over, and the fact that Bennu's rotation rate also increasing, thermal stress could also fracture some boulders and release some maybe trapped gases or some volatile material, and also with dust with them, sort of like what's happening in a comet. And also some places where it could get hot, it could be some water vapor. So we don't know exactly what's causing this. These three other current hypotheses. And also it could be due to we could also we might be able to observe some meteorite showers, which are now named Bennites, in the southern skies, but we don't have any results on this so far. Although this was also a concern from the spacecraft in the beginning, but it was estimated further that the spacecraft would not be affected this. And one of the interesting scientific results of this discovery was that we were able to even better constrain the gravity of the Bennu using by tracking the orbits of the particles that would fall back to Bennu. So it was very, very interesting, and it helped us to even improve the gravitational model we have. And also, of course, some particles would hyperbolically escape, but some of them would fall back to Bennu. Okay, now let's talk about the main core of the mission. So to sample. So to get the sample, there are four main axes, I would say, that we were very careful about, which is the deliverability, one of which is deliverability. So this is to be able to get the spacecraft to an area where we think would be interesting to come to sample. And also the scientific value of this area should be quite primitive material, as we want to bring back the material that from which the planets formed in the other solar system. And also sampleability. So being able to sample, the sample should be very loose material with maximum about 2 centimeters in dimension to be able to get into the sample sampling device. And also the safety is very important, because you don't need to go somewhere and where a lot of boulders are present and get hit by the asteroid, get the spacecraft hit by something and jeopardize the whole mission. So these were the like 4 matrices that led the sampling efforts, and there were about 4 different maps, and the convergence would be the best results. Yeah, so if you look at Bennu normally, I mean, it has surface like this, so it's everywhere it's spawned with a lot of rocks. Here again, yeah, so it's quite hard to pick an area, but there are like few areas there appear to be very relatively less populated by boulders, like here. And also, so we ended up with 4 sampling areas. So these were called the 4 final candidate sampling sites across Bennu, which are craters actually, because we think craters would give us fresher material that was exposed recently from Bennu, and which has not undergone effects like space weathering as much as other areas on Bennu. So first we came up with 50 candidates. There were a lot of efforts even online through CosmoQuest, and with citizen scientists participating, and and also we used some machine learning algorithms to find sites. And then there were like 50 sites, and from which we narrowed down to 16, and even from 16 we got to 4 sites, which are called Nightingale, Osprey, and Sandpiper and Kingfisher. So you can see them here. So each of sites is at different locations and has different characteristics. So if there are 2 at the equator. So here you see in the Osprey and Kingfisher at 11 north latitudes, and there's one in the north latitudes, northern latitudes at 56 north, and there's one at 44 south. So we did 4 reconnaissance or flybys to even further understand the composition of these 4 craters before choosing one final site and one backup site. So here again, the 4 are the locations that you would see in a map. So here is the Nightingale. It has the lowest albedo, so it emits very less light compared to it reflects very less light compared to the others, and it has a lot of color variations, so a lot of composition diversities and finest grains among the others, among the other sites. And here is the Kingfisher. So because it's smaller than the others, could be the younger, and also it has the highest aquical duration. So here is Osprey, and you could see in the circle, it's circled here, different angles. And this site has the strongest signal for organics. So these are some spectral signatures around 3.4 microns, and also is the brightest. So it has the highest albedo, and also has color variations. So we are sure to bring back sample with diversity of material. And here's the sandpaper at the 4th site, and it's could be containing some ejector from a different crater nearby, and it also has hydrated material. And yeah, it's the 2nd highest albedo variation crater. So it was finally decided that Nightingale would be the first prime site to go at. So here you are seeing this crater, which is about 20 meters wide, and the spacecraft to the right proportions. And just you have to also be careful that these big rocks here are around, so you have to be careful when you get the spacecraft to this crater. And the backup site, Osprey, here, also with similar dimensions. So we did a checkpoint rehearsal in April 2012, last year. So this was to you make you are in orbit around Bennu, and then you make one burn, and then you come cross to the surface, and then you mesh a certain area on the surface, and then like you fire again and you back up. So the image on the right is you can see the sample tags some instrument extended as if it were going to collect samples. So this was taken at about 70 meters altitude over Nightingale site. So here I'm showing you what happened actually. So this is last October, as we did touch the sample. So I would let it play a few times. So you could see the sample, and like as you touch, a lot of gravel and a lot of things are shaken, and a lot of material is released, and also we've collected some of the sample, and the mission target was to collect 60 grams of sample, and we think we successfully achieved this. And so here is a bit slower version, just to let you see what happens. So as soon as the surface is touched, the spacecraft goes a bit underneath, and then it fires. It releases the nitrogen gas from its gas bottles, which are in this box, sort of a covered box area on the instrument, and then a lot of energy is released, and you keep still going under the surface, and then as a few seconds later the retrofires would fire, so you would cancel your velocity, and then you would increase, and you come back from the surface. Yeah, so this is what we saw. I think if you've seen if some of you have seen what happened at Hayabusa, or at the Ryugu asteroid by Hayabusa 2 mission, you could have a similar insight of what would happen here. And so what we discovered was that actually there was a plan to measure the mass using an inertial experiment, doing a rotation with the extended arm after we've captured the sample. But the first images taken after taking the sample revealed that there was more material than expected, and some of them being escaping to the space. So it was decided that we would not even add a further rotation, and if we were to do this measurement of spin, it would even lose more material. So it was immediate after while it was decided to store the sample as soon as possible. So here you are seeing the sample being put here inside, and this is sample return capsule being closed, and just before coming back to just prior to leaving the Bennu for Earth. So just even though this was not included in the original mission, it was decided finally to go back and look what happened. So here is the Nightingale site before and after. So you could see this circle inside and circle outside the crater. So this is some rubble that was tracked to be moved by this impact touch and go of the instrument. So the mission is confident that it collected more than 60 grams of material, and the sample is now on its way to Earth expected to arrive in 2023. So yeah, only the time will tell us what's inside the sample, and to confirm all the hypotheses that we've come up using the data we have already examined. So it would also help us understand and better constrain the formation models of the solar system, especially if there were any pre-solar grains present. Using the facilities that we have on the terrestrial laboratories, we could even further study. And also there's an agreement between NASA and JAXA. They would share the samples. So the Hayabusa 2 mission returned samples from Ryugu, and this would be shared with NASA, and also from NASA they would share the samples with the Japanese community, and also around the world. And also more samples will be stored for future generations to study using the techniques that are not even thought of today, that would be elaborated in the next decades or even next centuries, just like it was done with the Apollo samples, which are still being examined and are still being stored for future generations. So that comes to the conclusion. Thank you. You can follow the mission on this social media as well if you like. Thanks a lot.
Thank you so much, Dej, for that really nice overview of the Bennu and also your work. So I do have 3 questions from Twitter, those who are listening in. And let me actually start with this very interesting question. Ueno-san is asking, it looks like a he's saying it looks like a deep fried cheese ball, the photos you showed of Bennu, because in Japan we have these deep fried cheese balls. So it looks like a deep fried cheese balls.
I never tried one, but okay, one day.
Yeah. And he's asking, whether the photos you showed has the real colors or are they black and white?
They are black and white. I mean, they are grayscale images. So if you were to make real colors, you need to, some of them were integrated using a longer wavelength range. And some of them were taken at, at a certain specific wavelengths. For example, like if it were an image from the map cam, which has 4 filters. So one is at V filter, so there is about 550 nanometers. So we only take the energy that is reflected at this wavelength with a short band pass. So and if you combine these sort of 4 images at different wavelengths or 3, you could make what we call a false color image, which helps us to understand the composition and in which areas which color is not present. So from this, you could say this is in this area, this is less rich in, that's reflected in this wavelength. So what I saw were grayscale images, all of them, of the surface. I don't know if it helped understand better.
Yeah, thank you so much. I think it would be good if you can stop sharing and turn on your video for the Q&A session.
Okay. All right. Let me get that. All right. It should be okay. Yeah.
Great. Okay. And Ken, if you see any questions on YouTube, let me know.
Okay.
Yeah, none at the moment.
Okay, thanks. Okay, so there's another question. During your talk, you referred to the asteroid as an active asteroid. What characteristics should define what is an active asteroid? I thought asteroids are all dead rocks.
This is what we actually what we thought until like I don't know a few decades ago. Asteroids seems to be like this dull, boring objects has no excitement. So all of a sudden, people discovered after repeated observations, of course, at some areas when they because of these orbits, sometimes it could be a bit elliptical. These are not perfect circles. At some areas, they're closer. So you're coming to a perihelion and you have a aphelion for any orbit, which is not a perfect circle. So in these cases, you get closer and you get like heated up more. And then you have liberation of some trapped, let's say, volatiles that would, like burst up and then sort of like if the material is very porous, it could like just like a jet, just like throw out and blow away like dust, and it could, because of this liberation, it could give rise to dust being observed. So this is a sort of a new sort of continuum of objects called active asteroids. There are like between comets and asteroids. So these are observed in the asteroid belt, and there are more and more objects like this being observed, and this is an ongoing research to better constrain what happens to these objects and how they become like this. Even like, but it's like series. You see deposits of salts, and this sort of like indicates some processes going on the surface. These are not like forever like inactive.
Great, very interesting. Yeah, I guess most of the public could imagine when you say every time an asteroid or meteorite, like inanimate, dead pile of rock. Yeah.
Yeah, this is like what we told in high school. You have to update the textbooks.
Yeah, exactly. Yeah. And okay, and the last question I have is about your career. Sato-san is asking, why are you particularly interested in studying Bennu? Why especially this object?
Well, Bennu, it was chosen as a candidate for, among others, there were like several objects, like because the first question at the beginning of the mission was to bring back a sample that would be primitive. So what is primitive? We would associate it with spectral class C, which is the carbonaceous bodies, of which B is a subtype, which Bennu is. So we identified, let's say you could first identify these asteroids, which would reflect less light, which is carbonaceous. And so among these objects, then you have to like understand which one you want to go. So you have to have some data. You have to have some idea to build a space mission. You have to have idea of the dimension of the body. So you have to take. So you have to understand how big it is. So you have to get some radar data. It is not possible to get the radar data for all the bodies. So you would come to get the radar data and make shape model for the ones that will make some flyby close passages to the Earth. And also then you have to also consider the energy that is required, the orbits. So we talk with the delta V's. So this is the how much of the change of the velocity you need to make to arrive, do a transfer from your orbit, terrestrial orbit around the Earth, and then from this orbit to the asteroid's orbit and come back. So in terms of this energy budget, what would be the most approachable? So you begin to put the first constraint by the priority, which is you need to bring primitive materials, so the C-type objects, and then what the dimensions are, and like what would fit better, and then the budget of the delta V, so energy that you need in your spacecraft. So yeah, so in this case, Bennu was chosen as one of those objects finally, from a pool of bigger objects of similar characteristics.
Yeah. Okay. Is there anything at your end?
Nope.
Okay, great. I think it's time to wrap up. We are just about the 1 hour slot. So let me thank the speaker today first. Desh, thank you so much for joining us from Rome. And it's morning for you, your daytime, and to share your enthusiasm with this really exciting mission, which is actually going to get much more exciting next year when you have the result, when you have the samples back to Earth.
Yeah, in 2 years now. Yeah. Thanks a lot. Thanks for having me. It's a pleasure.
Great.
Thanks for the questions.
Excellent. So, and before we sign off today, I want to share my screen to announce next event. Ayako-san, can you see I think you can see my screen. So I mentioned that Tokyo Space Cafe has 2 versions, the English edition, which is that you joined today, and then we have the Japanese edition. And next event will be on July 10th from 5:30 to 7:30, but the doors opening at 5. And this time we have Rinka-san from University of Tokyo, and it will be about mathematics. So I hope all of you could join if you can understand Japanese. And this event will be on site, but for a limited number of people. So I recommend to book your place as soon as possible and join the Japanese edition of Space Cafe next month. Okay, thank you so much for everyone joining today in your morning or evening or wherever you are joining from. So we hope we'll see you all next month as well with another speaker with another exciting topic. Thank you. Have a good day.
Thanks.